This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2019 AP Calculus exam, free response question BC5, namely partial fractions. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing why we need this technique of integration, and then present the general method or theory of partial fraction decomposition. I'll briefly remind you about long division involving rational functions, and how that procedure is related to partial fractions. And then I'll focus on the AP Calculus exam topic, partial fractions involving distinct linear factors. I'll try a few examples, one involving 3 distinct linear factors, and one involving the difference of 2 squares. And then I'll leave a few examples for you to try. The objective here is to develop a method for integrating a rational function, the quotient of 2 polynomials. The general method for solving this type of integration problem is to rewrite the rational expression as a sum of simpler fractions, called partial fractions. And then, theoretically, we know how to integrate these simpler fractions. To illustrate this method of finding simpler fractions to integrate, first, consider adding 2 fractions by finding a common denominator. Here, I added 2 over x minus 3 and 1 over x plus 2. I found a common denominator, and I ended up with this rational expression. Now, suppose I started by considering this integral. Since I know how to write the rational function as a sum of simpler fractions, I can rewrite the integrand. And then I can integrate term by term. And each of these antiderivatives is a natural log, by almost inspection. Technically, I guess, each is solved by a simple u substitution. To understand the method of partial fractions in general, let's consider a rational function. Here, f of x is equal to p of x divided by q of x, where p and q are polynomials. First, remember that if we have a polynomial p in this form, where a sub n is not equal to 0, then the degree of p is n. If the degree of p is less than the degree of q, then the function f is called proper. And it's always possible to express f as a sum of simpler fractions, rational functions with denominators of lower degree, provided that the degree of p is less than the degree of q. If the degree of p is greater than or equal to the degree of q, then f is improper. In this case, we divide q into p using long division, until a remainder r of x is obtained, such that the degree of r is less than the degree of q, where s and r are polynomials. And sometimes this preliminary step of long division is all that's necessary to complete an integration problem. Here's a quick example to illustrate how long division helps solve an integration problem. Let's see if we can find this definite integral. The integrand is a rational function. The degree in the numerator is 3. It's greater than the degree in the denominator, 1. This suggests that we rewrite the integrand using long division. Now, I won't go through all of the algebra, but here's the result of long division. And now I can integrate term by term, using the power rule, and a simple u substitution to obtain a natural logarithm. Here's an example of how we can use technology to illustrate some of the steps in this solution, and to obtain the antiderivative. The TI-Nspire has a built-in function called prop_frac, for proper fraction. And using this command, the TI-Nspire carries out the long division. And using the TI-Nspire, I don't really need to do the long division first. I can simply evaluate the indefinite integral. And here's the final symbolic answer. And that's pretty cool. If the denominator of the rational function is more complicated, then the next step is to factor q of x completely. It can be shown that any polynomial q can be factored into products of linear factors and irreducible quadratic factors. And here's an example. We can factor x to the fourth minus 81 into x minus 3, x plus 3, times x squared plus 9. Here, each term is raised to the first power, and x squared plus 9 is an irreducible quadratic. For each linear factor of q of the form ax plus b raised to the m power, the partial fraction decomposition must include these m fractions. That is, each linear factor of the form ax plus b to the m contributes these m terms to the PFD. Now, some of the capital A's, the constant capital A's, they may be 0, but we need to account for or consider all m terms. Notice we don't know how to find these terms yet. And for each quadratic term of the form ax squared plus bx plus c raised to the nth power, the partial fraction decomposition must include these n terms. Now, again, some of the constants, the capital A's and B's, may be 0, but we need to consider all n terms. Now, I admit that this decomposition might seem a little strange. However, a theorem in algebra guarantees that for any proper rational function, we can always find this partial fraction decomposition. The only type of partial fraction decomposition that students are responsible for on the BC Calculus exam is one in which the denominator is the product of linear terms raised to the first power. So let's see if we can evaluate this definite integral. Well, the degree in the numerator is less than the degree of the denominator, so we don't need to do any long division. So we'll factor the denominator completely, and it factors into 3 distinct linear factors, all raised to the first power. Each factor contributes only one term to the partial fraction decomposition. So now we know that the integrand, the rational expression, can be written as a sum of 3 terms in this form, where a, b, and c are constants. So the next step is to find those constants, a, b, and c. First, find the least common denominator on the right side, which is the product of the 3 linear terms, and write the right side as one fraction. If 2 rational functions are equal, and their denominators are the same, then their numerators must also be the same. So next we equate the numerators. And I did a little simplification to arrive at this expression. Since these 2 polynomials are equal, their coefficients must be the same. For example, the coefficient of x squared on the left side is 1, and this must equal the coefficient of x squared on the right side, which is a plus b plus c. So next, we equate all of the coefficients. If we equate the coefficients, this leads to a system of equations. That is, 3 equations and 3 unknowns. Now, we should be able to solve this system, and I won't go into the details here. I think you can see that we can find a pretty quickly. And then using this value, we can get a system of 2 equations and 2 unknowns, b and c. And solving that system is pretty routine. So, here are the solutions for a, b, and c. And now I can rewrite the original integral using this partial fraction decomposition, and then integrate term by term. In the second and third terms, there is a simple substitution of u equal to x minus 1, and then u equal to x plus 4. But each substitution leads to an antiderivative involving the natural logarithm function, which is very common in this type of problem. You might consider a graph of the original integrand and the antiderivative, just to visually confirm the graph of a function and its derivative. Here's how we might use technology to see some of the steps in the solution and the final antiderivative. Using the TI-Nspire, first I defined the function f. I can use the built-in function expand to find the partial fraction decomposition. And using technology, I really don't need to execute this step. I can simply evaluate the integral. This solution looks a little different than mine on the previous page. And that's because the TI-Nspire displays the final answer, in this case, with a common denominator, and by using some properties of logarithms. Now, there is an alternative method for finding the constants. Solving a system of equations always works, but this method can be faster. By equating the coefficients, this equation is true for every value of x. So we simply select values of x that simplify this equation. And specifically, we consider the zero of each linear factor. If we let x equal 0, which is the zero of the linear factor x, then the equation becomes minus 2 equals a times minus 1 times 4. And solving for a, we have a is equal to 1/2. Similarly, let x equal 1, the zero of x minus 1. We get b is equal to 2/5. And finally, let x equal minus 4, and we find c is equal to 1/10. This method works nicely if we have distinct linear factors in the partial fraction decomposition, which is the only case tested on the AP Calculus exam. In other cases, we might use a combination of techniques to find the constants. But again, the method of solving a system of equations always works. I'd like to consider one more common example, and this problem involves the difference of two squares. Let's see if we can evaluate this indefinite integral. The integrand is a rational function, and a good candidate for partial fractions. So we factor the denominator completely. And here, x squared minus a squared is equal to x minus a times x plus a. Each factor is linear, raised to the first power. So each factor contributes one term to the partial fraction decomposition. So I can write the rational function as a sum of two terms, like this. Use the common denominator on the right side and equate the numerators. Now use the zero of each linear factor for x. And here I have the values for the constants, in terms of that arbitrary constant, small a. Now I can write the original integral using this partial fraction decomposition. And I factored out the constant 1 divided by 2a, just to make things easier for me. We integrate term by term, and each antiderivative involves a natural logarithm after a simple u substitution. And I used a property of logarithms to write the final answer. And here's how I used technology to evaluate this definite integral. And I did this in two steps. First, I defined the function f, the integrand, and then I simply found the indefinite integral. Finally, here are a few examples for you to try. Each of these integrals involves a rational function and will require the method of partial fractions to find a solution. I hope this video provides some insight into the method of partial fractions and a few extra AP Calculus type problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.